we will discuss about the developments leading to a new, more suitable and more open model of structure of atom. So that is, we were, as I have already discussed earlier, we have come across with many structure of atoms proposed by different scientists. As science always accommodates whatever contributions given to science so far, and it will be part of it. No change from that. That means it will not throw away anything. Once something is contributed, it will be part of science. Just like history, it will be part of science. So we have learned about Thomson's atom model. It has got drawbacks and it has got some contributions also that put some light into the idea about the structure of atom. And then, in order to overcome its failure, Sir Rutherford came to the front row, and he had also given his own ideas and contributed his own share in designing a structure for the atom. And later, his own student tried to overcome the drawbacks that was part of Rutherford's atom model. Niels Bohr contributed with a bit more important or bit more clear idea about the structure of atom. Still there was problems we have seen and the drawbacks regarding Niels Bohr's atom model, and so we are moving further because it is a continuous journey of finding out what is true or what is real, that is what is science. So from Niels Bohr's atom model, the Bohr's atomic model, we are moving again with a contribution given by two other important aspects. These are the aspects that was leading to a bit more clear and convenient idea about the structure of atom, that is quantum mechanical model of the atom. So in order to reach to that quantum mechanical model of atom, two different aspects has contributed a lot to chemistry. That's what. First one is dual behavior of matter and Hazenberg's uncertainty principle. These are the two principles or two ideas that helped us to move towards a better understanding about the structure of atom. So we will discuss about in detail. Now, scientist de-Broglie suggested as electromagnetic radiation has a dual nature. We have discussed that earlier. That means electromagnetic radiation has wave-like nature as well as particle-like nature. So, just like that, matter also has two types of characteristics, or it will show two nature, dual behavior. So, that is wave-like nature as well as particle-like nature. So, he could bring out a relationship related to that. Now let's see the relation that connects the dual behavior of matter, just like electromagnetic radiation. That is, the particle nature as well as the wave nature is connected in a single equation. That is, according to Planck's quantum theory, E is equal to h nu. According to Einstein equation, E is equal to mc square. You know that. So we can write mc square is equal to h nu. Okay. And you know that nu is equal to c by lambda. So we will apply that here. mc square is equal to hc by lambda. So this c and c can be cut away. So mc is equal to h by lambda. Okay. So lambda is equal to h by mc, where m is the mass of the particle of any matter and c is the velocity of light. So if we take a velocity, instead of the velocity of light, velocity of any particle, we can write lambda is equal to h by mv, where m is the mass of the particle and v is the velocity of any particle. That we can also write lambda is equal to h by p, where p is momentum, mass into velocity. P is equal to mass into velocity. So lambda is equal to h by p. That is the relation that connects the wave nature of matter as well as the particle nature of matter, where lambda stands symbolizing the wavelength and p stands for symbolizing the particle. That where m is the mass of the particle and v is the velocity of the particle. Well, this relationship is known as de-Broglie equation. The equation that connects the wave nature of matter as well as the particle nature of matter. And so, what is the significance of this de-Broglie equation? Let's see. According to de-Broglie equation, we can use it. Actually, it is applicable for all material objects. Okay, but its significance is it's only applicable, able to prove the relationship of wave nature as well as particle nature, or the existence of wave nature and particle nature in the case of microscopic particles. That means it is not applicable for macroscopic objects. It has no significance in everyday life. So let's see how it is, how we can prove that it is applicable only for microscopic particles, but it is not applicable for macroscopic particles or bigger objects. Well, let's see an example to explain the significance of de Broglie equation, which is applicable only for microscopic objects. Let's see a question. The velocity associated with a proton moving in a potential difference of 1000 volts is 4.37 into 10 to the power of 5 meter second inverse. If the hockey ball of mass 0.1 kg is moving with this velocity, so the hockey ball is having the velocity 4.37 into 10 to the power of meter second inverse, and this part is just to make you confused. From here the question begins, right? So here you see, if the hockey ball of mass 0.1 kg is moving with this velocity, so we are dealing with the hockey ball which is having weight or mass 0.1 kg and it is moving with this velocity 4.37 into 10 to the power of 5 meter second inverse. Calculate the wavelength associated with this velocity. So we have to find out the wavelength associated with the velocity given for the hockey ball. So let's see, velocity of the hockey ball is 4.37 10 to the power of 5 meter second inverse and the mass of the ball is 0.1 kg. So it's enough to find out the wavelength. We have already the equation given by de Broglie. So lambda is equal to h by mv. We know the mass of the ball, we know the velocity of the ball, and we know the Planck's constant value h, that's 6.626 into 10 to the power of minus 34 kilogram meter square second inverse divided by mass 0.1 kg into 4.37 into 10 to the power of 5 meter second inverse. That is the given velocity. So we will get the value 1.52 into 10 to the power of minus 38 meter. And this wavelength is very difficult. By using any means, you will not be able to measure this wavelength. Okay, that is so much a negligible value. It's very small value which you will not be able to measure by using any means. That means de Broglie equation is not applicable for macroscopic objects or bigger objects. It is applicable only for microscopic particles. So this is the end of our session today. Thank you very much. See you again with new concepts and examples and explanations.